Well, we have been talking about the initial phases of fatty acid beta oxidation. Last time we talked about what happens to triglycerides. They get hydrolyzed by lipase. We talked about the fate of glycerol. Today we're going to deal with the fate of the fatty acid. Fatty acid is a carboxylate. That's a level 4, pretty low on our reactivity as an electrophile. In fact, the fatty acid is more of a nucleophile because it's electron rich at the negatively charged carboxylate. And we were talking about this reaction that is necessary to prepare the long-chain fatty acid for what's called beta oxidation. Ultimately, we're going to clip each of these 2 carbon units from the fatty acid to become acetyl-CoA, and that's going to go to the citric acid cycle. But in order to do that, we need to convert the fatty acid into a thioester. That's level 1 reactivity. So that's uphill from carboxylate to thioester. Therefore, it's no surprise that we're consuming ATP in this reaction. And you will see actually that the way the reaction works, we end up consuming 2 equivalents of ATP, even though it looks like we've only consumed 1. I'm going to make the math work at the end of it, but let's work on the mechanism first. We're going to use, as I said, ATP and coenzyme A. The enzyme that does this is called long-chain fatty acyl-CoA synthetase, or ligase. This is an enzyme that makes a long-chain fatty acyl-CoA, or thioester. And the term synthetase refers to an enzyme that uses ATP to synthesize something. The extra T in the synthetase is, I think, for the ATP. Who knows? Coenzyme A, I think you've seen before. I'm drawing it again here for your viewing enjoyment. It's actually a long, complicated molecule. The business end is the thiol, and that's the portion that's linked to the carboxylate in the thioester. You can break apart coenzyme A into 3 different parts. This end comes from ATP. You've got the ribose ring, the adenine base, a couple of phosphates on the 5' hydroxyl group, and an unusual phosphate on the 3' hydroxyl group. Then you've got this segment here, which is called pantothenic acid, and that's actually vitamin B5. So you eat that, and your body uses it for this purpose. And then this 2-carbon aminothiol is actually derived from the amino acid cysteine. If you imagine a carboxylate being there, then you've got cysteine, and it's probably a PLP-mediated decarboxylation, like we saw before, to make dopamine and serotonin that's involved to make this 2-carbon aminothiol. Okay. So we started this last time. The carboxylate attacks the alpha phosphorus as a nucleophile. The enzyme activates the alpha phosphorus. Magnesium probably helps the pyrophosphate be a good leaving group. You get this pentavalent intermediate where phosphorus is bonded to 5 things. Then electrons kick down, pyrophosphate leaves, and you have an intermediate called the fatty acyl AMP. It's an acyl phosphate. That's now level 1 reactivity. All of this can be seen as a decent leaving group. So we use ATP to convert the carboxylate into an acyl phosphate, an acyl AMP. Now this is a good leaving group, and now the carboxylate is prepped for nucleophilic acyl substitution. Another thing that helps this reaction is that the pyrophosphate leaving group subsequently gets hydrolyzed. I don't actually know whether this happens spontaneously in water at some rate or whether an enzyme is necessary to catalyze it. In any case, it's very exothermic. It's downhill. The phosphate itself is about the same level of energy as the carboxylate. So hydrolyzing a pyrophosphate to a phosphate is a downhill reaction. Go ahead.
I might have missed something, but what do you mean by the different levels of reaction?
So yeah, let me just go back to that. We talked about that briefly last time, sort of ranking carbonyl and phosphoryl compounds in order of reactivity. Up at the top, you've got thioesters, acyl phosphates, and AMPs, aldehydes, ketones, ATP, phosphoanhydrides. Next, you have esters and phosphoesters, then amides, then carboxylates and phosphates.
Okay, thank you.
Yeah, so you'd predict, since these are pretty unreactive, they actually might be decent leaving groups. And the reasons these are reactive is because after a reaction, they give good leaving groups. Yeah, okay. Others? So only halfway through the reaction, we now need to use coenzyme A as a nucleophile to replace the AMP group so we can get the thioester. And the thioester is the substrate for the next reactions. This part is easy. This is just nucleophilic acyl substitution. And you will have likely seen this before. So we'll show the fatty acyl AMP, we'll show coenzyme A, and I'm only going to draw the thiol portion of it. Abbreviation is always appreciated in biochemistry. The enzyme, a base from the enzyme active site will deprotonate the coenzyme A thiol. Then it will attack the carbonyl carbon to give a tetrahedral intermediate. I'm going to now abbreviate everything that was in green as OAMP. Then electrons will kick down and kick off AMP as the leaving group, and that will give us our fatty acyl thioester. And then here is AMP with the ribose ring and the adenine base. Okay, it's the same enzyme that does both of these things. So the enzyme binds ATP, then it binds the long chain fatty acid. There's actually a tunnel that the long chain hydrocarbon chain packs into in the active site. The carboxylate attacks the alpha phosphorus, you get the AMP intermediate, then coenzyme A comes in and does the attacking at the carbonyl carbon. All right, let's talk about math. I told you that this reaction consumes basically 2 equivalents of ATP, even though there's only 1 in the reaction mechanism. How do you explain that? Well, in this reaction, we go from ATP to AMP, and we end up hydrolyzing pyrophosphate. So in a way, we've broken not 1, but 2 phosphoanhydride bonds. We broke the first when we attacked the alpha phosphorus and pyrophosphate left. We break the second when water adds to the pyrophosphate to give you 2 phosphates. The other way to understand this is to realize that AMP in itself, so ATP is generally, ATP is generated from ADP and not from AMP, right? There's substrate level phosphorylation that happens in glycolysis, and then there's also oxidative phosphorylation that happens in the mitochondria and the electron transport chain. In both cases, the starting material is ADP, not AMP. So how do you get, if you have AMP, how do you recover ATP? And the answer is there are enzymes that will take AMP plus ATP and generate 2 ADPs, and then you can regenerate 2 ATPs from that. So you need to think of this reaction that I've shown you up here as basically consuming 2 equivalents of ATP. And that'll be important because later on we're gonna do just a little bit of calculation to figure out, okay, how many ATPs do we get from this fatty acid? Okay, questions about that? Yes?
So in this scenario, it was attacking on the alpha.
That's right.
The previous example, talking about it attacking on the gamma.
Right, when we do kinase type reactions, such as when we were modifying glycerol, the glycerol alcohol attacked on the gamma phosphate. So kinases activate the gamma phosphate for attack. The acyl AMP, or the fatty acyl-CoA synthetases activate, now I can't find where I was. The fatty acyl-CoA synthetases activate on the alpha phosphate. And that difference will just be how the ATP binds in the enzyme active site and what functional groups are around it. Okay, others? All right, let's do beta oxidation. This is really cool because there's some chemical logic to it. So this is called fatty acid beta oxidation, and you'll see why in just a little bit. So we've already got our fatty acyl AMP, and I'm going to draw the two, not all of the fatty acid, but just the two carbon, or the four, still I'm struggling, sorry folks. Let's draw the last four carbons of this fatty acid, and then we'll do an R for the rest of the molecule, 1, 2, 3, 4. Okay. So the first step is an oxidation step, and it's kind of an unusual one. We'll have a base from the enzyme remove the alpha proton to make an enolate. And then, and then the electrons on that negatively charged alpha carbon will kick down and have hydride be delivered to a reducing agent as a leaving group. The reducing agent, or rather the oxidizing agent that's going to accept the hydride, is not NADH, but it's a molecule called FAD. And you may not have seen FAD before, so we'll draw it for you now. It's way more complicated than NAD+, so it's a pain to draw. There are two nitrogens here, 6-membered ring there, a double bond there, another 6-membered ring here. FAD stands for flavin adenine dinucleotide. And if you've heard of vitamins like riboflavin, then that's what this refers to. This is the ribose ring. Then there's a 5' hydroxyl group. And I'm just going to draw this for you once so you can see the structure, and then ever after we will just abbreviate it because nobody wants to draw all of this. Then there's a second ribose ring. And then there's A. So the F stands for this group, which is called flavin. This A stands for adenine, and then the D stands for dinucleotide, which is what you get when you have base plus ribose plus phosphate. So you can see the two nucleotides. There's this one, and there's this one, and they're linked together via a phosphoanhydride bond. So FAD, it's a little bit less clear to see how it's an oxidizing agent. With NAD+, we were able to see, oh, hey, look, there's a carbon that's electron poor. With FAD, it's a little bit more complicated. The hydride gets delivered to this nitrogen. You can envision that nitrogen as electron poor because it is conjugated to two carbonyls. Do you see how this nitrogen is at the beta position of an alpha-beta unsaturated carbonyl compound? Carbonyl carbon, alpha carbon, beta carbon. I could temporarily draw a resonance structure that would look like this, that would put a positive charge on that carbon. That sort of, you see that? Similarly, the nitrogen is actually also conjugated to this carbonyl carbon, alpha, beta, gamma, delta, and conjugated all the way. So I could draw a resonance structure that would look like this, oops, with a negative charge on this carbonyl carbon and a positive charge on that nitrogen. So by resonance at least, that nitrogen is electron deficient and it can accept a hydride. When it does, electrons are going to kick down here to form a pi bond, and then this nitrogen is actually going to pick up a proton, probably from some acidic group on the enzyme. The product of that step, of that reduction step, is going to be our oxidized thioester. Yes, no. Let me see if I drew that right. 1, 2, 3, 4. Yeah, it's good enough. All right, the product is going to be our alpha beta unsaturated thioester. And then a molecule called FADH2, which is going to be just like FAD, only it will have the hydride on the nitrogen, and then it will have the proton that was gained from the other nitrogen below. So this in blue is the hydride that came from our enolate, and in green is the proton that came from the enzyme. And that's why you call it FADH2, because it's accepted both a hydride and a proton. Okay, the enzyme that does this is called, well, guess at the name, actually. This is an oxidation step, so guess what the name should be. Oxidase is a good guess, but remember, what we often call redox enzymes is dehydrogenases, because we've lost hydrogen, proton and hydride went to FADH2. So this is a dehydrogenase, and it's actually called, named for the substrate, acyl-CoA dehydrogenase. Okay. And the mechanism is basically E1CB type elimination. You make the enolate first, then you kick off the hydride. All right, and the product is an alpha beta unsaturated thioester. When you see this whole pathway together, you will see the logic in putting the double bond there. So this is sort of the first step of beta oxidation. Okay, so let's review what we know about alpha beta unsaturated thioesters. Where are they electrophilic? Where are alpha beta unsaturated carbonyl carbons electrophilic? 2 places. What are they? Beta and carbonyl carbon, right? You've seen nucleophiles attack the beta carbon before. You've seen nucleophiles attack the alpha carbon. The second step of fatty acid beta oxidation involves what we'll say is conjugate addition of water to the beta carbon. The enzyme that catalyzes this reaction is called enoyl-CoA hydratase, which is a weird name, but hydrate is embedded in the name of the enzyme, suggesting that we're going to add water to the molecule. And so this is how that process works. A base from the enzyme deprotonates water, and then deprotonated water or hydroxide attacks the beta carbon. Okay, now if this were a conjugate addition and we were drawing the mechanism, earlier this semester, we would break the pi bond and have it go onto the carbon, or go onto the alpha carbon where it could be stabilized by resonance, and we would draw an enolate intermediate, okay? In enzyme catalyzed mechanisms, it's sometimes unclear whether you have the enolate intermediate or whether that enolate intermediate actually gets protonated even as it's forming. So I'm never totally sure how to draw this mechanism. We could draw this step and then draw the enolate intermediate. Let me just draw real quickly what I'm talking about. Here on the beta carbon is the new OH group. And here is the enolate. Do you see how that would be the intermediate of what I drew before? But it's also sometimes common for one of the ways catalysis happens is you protonate the negatively charged stuff even as it's being formed. And so some people, and I think it's a sensible thing to do, in any case it saves you time. Some people show the enzyme protonating the resulting enolate as it's happening. And that's always acceptable in enzyme catalyzed mechanisms. You sort of just, but you need to make sure you understand the basic chemistry and see how this is a conjugate addition reaction. Are there questions about what I did there? Are you okay with protonating the enolate at the same time as it's forming? I don't have a problem doing that as long as you understand how conjugate addition happens. All right, so our product is now a beta hydroxy carbonyl compound. And that should ring a few bells because you've seen beta hydroxy carbonyl compounds as aldol products before. But it turns out that nature isn't going to do a retroaldol reaction, in part because that wouldn't lead to a molecule that would be immediately useful. And nature's everything, nature's efficient. And so before you, once we get this beta hydroxy carbonyl compound, we're going to oxidize it with NAD plus to get a beta keto thioester. So this reaction is going to involve NAD plus. We're going to get NADH out. A proton will be removed in the process. Understand that I'm just saying a base removes a proton, not that a proton flies off into space. And the product that we get is this now beta keto thioester. And you should recognize beta keto thioesters because, or you should recognize at least beta keto carbonyl compounds because we've said that they are the products of Claisen reactions. And nature at this stage is set to do a retro-Claisen reaction that is going to break the bond between the alpha and the beta carbons. Real briefly, though, I told you I wouldn't do it, just as a reminder of the NADH mechanism, or sorry, the NAD plus mechanism. This is the structure of NAD plus. A base from the enzyme removes the proton on the alcohol, electrons kick down, and hydride is delivered to NAD plus, and then you can rearrange the arrows on NAD plus to get NADH and your beta keto thioester. Okay, do you guys remember the Claisen reaction? That's ancient history. You got nothing? Okay. I would recommend that at least in a couple of weeks you remember what the Claisen reaction is, okay? Put it on your list. Remember that the Claisen reaction is basically the aldol reaction of esters. So if we used this ester and we used ethoxide as a base, we could make a small percentage of the enolate. And then do you remember how that enolate could attack the carbonyl carbon of another ester to give you this tetrahedral intermediate? And then electrons could kick down and kick off ethoxide as a leaving group, and your product would be this beta keto ester. Vaguely familiar? That's sort of the aldol reaction for esters. The reason it's different is because in the aldol reaction you attack a ketone or an aldehyde and there is no good leaving group. In the Claisen reaction you attack an ester and there is a good leaving group. Okay? A retroclaisins don't generally happen in the lab because once the leaving group leaves, it's a strong base, and the proton that's alpha to 2 carbonyls is especially acidic, so that's sort of a thermodynamic sink. The retro reaction, which doesn't happen in the lab, would be if ethoxide attacked the ketone to give you this tetrahedral intermediate, and then the oxygen kicked off the enolate. We did retroaldol reactions. We haven't really done a retroclaisen reaction before, and the reason we didn't is that in the lab, the ethoxide would never attack the ketone, it would just remove the proton. Enzymes are able to control that a little bit better. And so we're set up now with this beta keto thioester to do a retroclaisen reaction. All right. Notice that in the Claisen reaction, the new bond that we made is here between the alpha carbon and the beta carbon. So if you were going to focus in on the bond that we're going to break in a retroclaisen reaction, it's the bond between the alpha and the beta carbons. Conveniently, if we broke that bond, you could see that we would liberate on this side acetyl-CoA. All right? So let's show you how that's done. This will be step 4 of beta oxidation. We're going to bring in coenzyme A as a nucleophile. And what's going to be, what the products will be, is this truncated fatty acid. By truncated, I mean it's lost 2 carbons. Truncated fatty acyl-CoA. And then the other product will be acetyl-CoA, which you can then take to the citric acid cycle. Okay? So how does that happen? The enzyme mechanism here is pretty well understood. There is a cysteine residue in the active site, and then a nearby histidine residue that acts as a base. So I'm just going to make a note here, active site cysteine residue. The base deprotonates the cysteine, and then the cysteine thiol attacks the beta carbon of the beta keto ester. The reason this can happen is that cysteine is not a particularly strong base. So that's one way the enzyme dodges the potential problem of a backwards Claisen reaction that I told you about if you're going to use ethoxide as a base/nucleophile. that alpha proton that's between two carbonyls is simply too acidic. Nature dodges that by using cysteine as a nucleophile. Its pKa is 8, not even quite a good enough base to deprotonate that alpha carbon. All right, so that's nucleophilic attack. Let's draw the intermediate that comes from that. Here's the negatively charged oxygen on the tetrahedral intermediate. I'm going to still label beta carbon, alpha carbon, carbonyl carbon. I'm going to highlight acetyl-CoA here. Here is the enzyme cysteine residue. And at this stage, electrons kick down from the carbonyl oxygen, and we could draw the enolate leaving as a leaving group, the acetyl-CoA enolate. That enolate would be resonance stabilized. But instead, we're going to show it being protonated by some acidic group in the enzyme active site as it leaves. That step here that I've drawn is the retroclaisen step. And if you compare it to the claisen before, it would be the backward step here, where electrons kick down and you kick off the enolate as a leaving group instead. All right, so let's keep going. We lose acetyl-CoA there. So part one of our mission for this step is accomplished. Now you do have a truncated thioester, but it's linked. This is the old beta carbon. I'm going to put it in air quotes. Those aren't air quotes when you write them, but I'm going to put them in air quotes to indicate that it's now the carbonyl carbon after the retroclaisen reaction, but this fatty acid is now 2 carbons shorter. Where did the alpha and the carbonyl carbons go? They went off with acetyl-CoA. What's left now is to basically liberate the truncated fatty acid from the enzyme. We'll do that using the coenzyme A thiol as a nucleophile. Some base from the enzyme removes the proton from coenzyme A, which attacks this carbonyl carbon. This is just nucleophilic acyl substitution. You're going to get this tetrahedral intermediate where the coenzyme A thiol is linked to the carbonyl carbon. Electrons kick down and leaving group leaves, and that then liberates your truncated acyl-CoA. All right? So in that process, we have clipped off the terminal, the 2 pink carbons, and we're left with a fatty acid that's 2 carbons shorter than it used to be. Right? And then we can go back to step 1. Then that truncated thioester can be oxidized and so on. Go ahead.
On step 4, why couldn't you just attack the nucleophilic acyl substitution with acetyl-CoA?
Yeah, the question is, why does the enzyme bother? Why couldn't we just have acetyl-CoA here instead of the cysteine? I don't know. But the enzyme does have an active site, cysteine. The short answer to your question is, if you think about it this way, the enzyme only has to find the fatty acid thioester to get started. It doesn't have to find both the fatty acid thioester and another molecule of acetyl-CoA. So maybe it's faster to bind and do the retroclaisen reaction to let acetyl-CoA leave, and then another molecule of CoA comes in. I don't know. It's really a question about evolution and whether alternative mechanisms would have been faster, and I don't know. Okay, other questions? So this process is iterative. As I said, once you get to the truncated acyl-CoA, you go back to step 1 of beta oxidation. And then you repeat until the last reaction, and the last reaction is going to be the one where you have a 4-carbon beta keto thioester. And once you do the retroclason, step 4 of the last reaction will give you 2 molecules of acetyl-CoA. All right? Does that sort of make some sense? All right, that's what people say when they mean burning fat. They mean lipase hydrolysis of triglycerides, glycerol gets phosphorylated, oxidized, goes to glycolysis, fatty acid thioester, and fatty acid gets modified to the thioester, and then iteratively truncated by this beta oxidation process until every 2-carbon unit has been clipped off as acetyl-CoA. So it can be helpful to maybe do a little bit of math to summarize. Each thioester, each fatty acid, when it shows up at beta oxidation, has consumed already 2 equivalents of ATP. So let's just consider briefly, let's do a 16-carbon, 2, 4, 6, 8, 10, 12, 14, 16. A 16-carbon fatty acid. And let's think about the yield in terms of energy-rich molecules that happen as this is broken up into 1, 2, 3, 4, 5, 6, 7, 8 molecules of acetyl-CoA. All right? So first, remember in this process, we're basically down 2 molecules of ATP because we have to activate the carboxylate as the thioester. That's the acyl-CoA synthetase. How many turns through the cycle of beta oxidation does this 16-carbon fatty acid pass? 7. You want to say 8 because 16 divided by 2 is 8. Why isn't it 8? Because there's only 7 bonds to break. Okay? So for a 16-carbon fatty acid, you're going to go through 7 turns of beta oxidation. Now, what were the energy-rich molecule yields of beta oxidation? Let's highlight them in yellow. The first was FADH2. That's orange, not yellow, but whatever. And the second was NADH. And that's it. So each turn of the beta oxidation gives you 1 NADH and 1 FADH2. Is that right? Did I do that wrong? I feel like that's right. So 7 turns of beta oxidation give you 7 NADHs and 1 FADH2. Now, oh, sorry, that should be 7 because we can't do math. All right. Now, what is the fate of those FADH2 molecules? It's thought that, and the NADH molecules, they can do a lot of things in biology, but in terms of, but one of the most important things they do in mitochondria is they go to the electron transport chain. They deliver electrons and hydrogen to metal centers or other molecules in the electron transport chain. That drives a proton gradient, which is then used to make, to drive a synthase that makes ATP. And people have done the math and found that on average, in the electron transport chain, that 1 NADH is pretty well good for 2.5 molecules of ATP. You have to, the analysis is kind of weird, and so you have to sort of trust the people that have done it, but it relates to how many electrons get transferred at what points and how many protons that causes to be transported across a mitochondrial membrane, and then what kind of proton gradient is needed to drive ATP synthesis. And then each FADH2 molecule is thought to generate 1.5 ATPs. So you can do the math and figure out, for 7 turns of the beta oxidation, you'd make, I can't do that math, 2.5 times 7 in my head ATPs, and 1.5 times 7 ATPs from FADH2. But that's not the total yield, because ultimately acetyl-CoA is going to go to the citric acid cycle, where it's going to be converted into CO2, and we're going to generate even more ATP and NADH. And so we're not yet even ready to answer the question, how much ATP can we get from this thioester? We're going to have to come back to this intermediate calculation to figure it out. By the way, you'll encounter different numbers for what people think the equivalence between NADH and ATP is. And so just make sure if you're doing a problem in a textbook, you know what their assumption is for how many ATPs you get from NADH versus FADH. Okay, so that is fatty acid beta oxidation. Now, what we need to do is talk about carbohydrate metabolism. And we could go directly to the citric acid cycle because this is a common pathway from carbohydrates. But what I'd rather do is go back to glucose. Now that we've seen the fate of a triglyceride, getting it all the way to acetyl-CoA, we're going to go back to glucose and see what happens to it to get it all the way to acetyl-CoA, and then we'll join those two pathways up at that point. So the metabolic pathway that initially deals with glucose is called glycolysis. And this happens in the cytosol of the cell, and it's sort of what you maybe have heard of when you hear about anaerobic respiration. This can happen in the cell even without the presence of oxygen. You need to breathe oxygen to drive the electron transport chain. Oxygen that you breathe is ultimately the acceptor of electrons that are delivered to the electron transport chain from NADH. Where did those electrons come from? NAD+ took them from the molecules that we're metabolizing. Glycolysis doesn't involve oxygen as an electron acceptor, but molecules from glycolysis can be taken to the citric acid cycle. So it's kind of a complicated metabolic pathway. There are like 9 steps, and you want to get a good feel for what the molecules are called, what the enzymes are called, and we also want a good feel, based on our understanding of carbonyl reactivity, which steps are super downhill in energy versus which steps are pretty much equilibrium steps. So in the first step, we start with glucose, and I'm just using a squiggly line to indicate that we're not really caring whether we get alpha or beta anomers. Start with glucose. Oops, wanted to move that over a little bit. Should have quit while I was ahead. This is a kinase reaction, so I won't draw the mechanism for you. The enzyme activates the gamma phosphate of ATP, and the enzyme that is called hexokinase transfers a phosphate from the gamma phosphate from ATP to the C6 hydroxyl group, which acts as a nucleophile. So we take a phosphoanhydride from ATP, which is reactivity level number 1, very reactive, and we convert it into a phosphoester on glucose. This is on carbon 6 of glucose, so this is called glucose 6-phosphate. You've gone from the phosphoanhydride level of reactivity to, what's this functional group? What would you call that? Yeah, that's right, it's a phosphoester. So that goes from level 1 reactivity down to level 2. So you expect this reaction to be exothermic, and it is. Estimates of what the free energy change of this reaction is sort of depend on cellular conditions, but a good estimate is about -8 kcals per mole. That's very downhill in energy for a reaction, probably enough to be what we would call irreversible. So once a glucose molecule enters glycolysis and is phosphorylated, it is committed because it can't go back. Because of that, the cell regulates the activity of this enzyme because your body is not interested in committing glucose to metabolism if it doesn't currently need to metabolize glucose. You will learn in biochemistry about how that enzyme is regulated. Yeah?
And then like a kilocal is just what we call a calorie,
Right,
right?
a kilocalorie is, as in kcal, is capital CAL, calorie on your nutrition. Now, the energy that's released in downhill, this is energy that's lost as heat. This isn't necessarily energy that you use to do anything, other than we're manipulating functional groups. You can see that, and you may be asking, what the heck are we doing? This process is supposed to generate ATP, not consume it. Wait, because nature's going to make back its initial investment and more. So this is sort of the investment phase of glycolysis where you have to commit an ATP in order to get things going. All right, with that, I think we are like sort of out of time, so we'll stop there. I will see you on Monday. Have a great conference weekend. Remember, the commandments are stars by which we guide our lives, not sticks with which we beat ourselves. Good luck.